Well, good afternoon, everybody, and welcome to this afternoon's webinar. This afternoon, I'll be talking to you about some of our ongoing work in the area of development of antimicrobial materials. And specifically, I'll be talking to you about the development of polyethylene-based materials which have antimicrobial properties. And in our current climate, materials that have got biocidal behavior are becoming of increasing importance globally. But today we're going to focus on microbes as a starting case for antibacterial materials. And this is a collaboration between EPSSC, P&G, IMSE and Imperial College. And the work we'll talk about is the work that's been performed by my PhD student, Fatima Alami. So a little bit of background here. We'll start talking to you a little bit about bacteria and biofilms. And bacteria are really ubiquitous materials. They are everywhere in our world. Bacterial species are really probably on many of the surfaces that we see in our regular world. And in many cases, we don't need to worry about them. But as we'll see, some bacteria are not very friendly, and we need to be concerned about those. And in certain environments, particularly hospital environments, medical environments, and certain production environments, we are very concerned about the potential contamination or introduction of bacteria into our process, into our materials, into our patients. And essentially, there are a number of stages in which bacteria will interact with materials. And from initially, they will start to absorb on the surface. Let me just find my pointer. You can see my point there. So initially, when bacteria attach, they will adsorb onto a surface. And after some period of time, they will start to irreversibly attach to the surface. And it is these early stages of bacterial interaction with materials that we are particularly interested in. So specifically, we are looking at processes by which we can retard, delay, defer, or undermine both the adsorption of bacteria onto surfaces and also their ability to attach to surfaces. Once bacteria are attached to surfaces under certain conditions, they will start to grow, divide, and actually form colonies. And those colonies are known as biofilms. But what we're trying to do is trying to intercede early on in the process to make the surfaces that the bacteria see are inhospitable. We're trying to provide surfaces that will, in the end, cause the bacteria to either not want to attach or to actually die in the process of attachment. So we're looking to change the way that bacteria engage with surfaces, and today our discussions around polymeric materials. But as I said, we're very interested in the early stage of the process where the bacteria first make contact with the substrate and how we can influence their behavior in this early stage of the interaction process. So today's presentation, most of the work, although not all the work, but most of the work will focus on a particular bacteria called Pseudomonas aeruginosa. It's a relatively common bacteria. It's described as being an opportunistic gram-negative bacteria. It's particularly prevalent in niche environments which are wet or moist. It is particularly dangerous for individuals who've got medical problems, and particularly those who are immunocompromised, people with cystic fibrosis, cancer, or AIDS. They are actually at some risk with these particular bacteria. And sadly, it's one of the most common causes of ventilator-associated pneumonia, which has sadly a very high mortality rate. And also, Pseudomonas is a very common member of the hospital bacteria community, and it's particularly prevalent in wounds and burns. So it's quite a common bacteria. And for people who are quite well, it's tend not to be a serious risk. But for people who are unwell or have a medical problem, it can be quite challenging and sometimes quite dangerous. It has a complication in that it is relatively resistant to a whole range of chemotherapeutic agents and antibiotics. So it's a relatively hard pathogen to entirely eliminate. So it's a candidate that we have focused on in our studies. And we can see a couple of images here. The one on the right just shows you an SEM image, a scanning electron microscope image, where the bacteria being colored in artificially just to give you some contrast. And on the left, we can see an artist's picture of what the bacteria would look like. And these would, as you could imagine them if they were in a liquid fluid and they were propelling themselves around. And just to help you with the dimensions here, these are 3 microns by just under 1 micron. And we'll see in a moment, a human hair is about 100 microns in diameter. So these are roughly, a 30th or a 40th the diameter of human hair. So they're not the sort of things that you're going to very easily see with your naked eye. Very difficult to see. And indeed, as we'll see in a moment, they can be difficult to see even without a naked eye, but just using advanced technology. So what I'm showing you here is a human hair fiber. It's about 80 microns across. A micron is a thousandth of a millimeter. And I've electronically, in this case, attached a couple of bacteria onto the surface there. And if you look very carefully, you might see the couple of bacteria I've attached to the surface. They're quite small. And if you look very carefully, you may have well spotted where I'm currently circling. And there are two little objects there which I've cut and pasted in. That represents the size of the bacteria. So they're quite small and they're very difficult to see with the naked eye. And indeed, we need microscopes to see them. And the techniques that we'll describe today, where we look at the way these materials are attached to surfaces, is very much based on advanced microscopic methods. So the polymer that we're going to be focusing on today is, in fact, the world's most common and indeed cheapest polymer. It's polyethylene. And you'll find the polyethylene in probably most houses in the world, whether it's the rubbish bags, it could be cups, containers, plastic materials of all sorts are often made out of polyethylene. So pipe insulation, wash bottles, food, liquid containers, plastic bags. Many materials that you buy food from in the supermarket, for example, will come in polyethylene containers. And these containers are manufactured in a very cheap way. They can actually be heated up to some extent to clean them. And they're also what we describe as relatively hydrophobic materials. These are materials that don't like water, because it turns out that polyethylene is made from a hydrocarbon. It's made from ethylene. Ethylene is a very hydrophobic material by definition. So what it means is if you put water inside these containers, the water is repelled away from the surface, just like water is repelled away from a Teflon surface. So these materials are very commonly used. They are also very inexpensive. So they're also found in lots of applications, such as disposable equipment, such as disposable gowns used in hospitals, and a range of disposable scientific and medical things are made from polyethylene. And it turns out that's going to be our base polymer that we're going to work on. And we're particularly going to work on what's known as high density polyethylene. It's a particular variant. It just means it has a slightly higher molecular weight and slightly higher density. But it's basically the same as most of the polyethylenes that you'd come across at home, in the laboratory, in the supermarket. So one of the challenges with a material such as polyethylene is it's very inert. Indeed, that's one of its attractive features. Its inertness means that there are lots of applications where it's ideal. But it turns out that we know from the literature and from experience that hydrophobic materials such as polyethylene are actually very compatible with bacteria. In fact, bacteria rather like hydrophobic surfaces like polyethylene. And as we'll see later on, they're quite well attracted to them. So of course, in our current project, we don't want that. So we want to change the material in a way so that it no longer attracts bacteria and ideally will start to kill them. So to do that, we've got to change some of the surface chemistry of polyethylene. So the polyethylene, as you saw before, is full of all these relatively inert hydrocarbon molecules, and we need to change those. So what we're going to do actually is use a technique for acid etching them. So we're going to take the polymers that we study in this particular bit of work, we're going to expose them to some quite strong acids. In this case, we're using a concentrated chromic acid. And what will happen is in that process, we will oxidize the surface. And that means we are going to add chemical groups to the surface that have oxygen. These could be oxalic, these could be carboxylic acids, they could be alcohols, but those groups will be chemically formed on the surface due to the action of the chromic acid we're using here. And chromic acid treatment and many other similar treatments are quite often used to treat polymers like polyethylene and polypropylene. That's because there are a lot of applications where you want to stick something to polyethylene. And hydrophobic materials are naturally not very sticky. So you can do that, you can change those adhesive properties by introducing some acid groups on the surface, such as carboxylic acids and alcohol groups. But for example, if you wanted to print on a polyethylene or stick polyethylene pieces together, you often have to treat the surface to allow that to happen. So we're going to be treating the surface in the current study to improve the acidity and change the surface chemistry in a way that we hope will facilitate an unpleasant experience for the bacteria. So we can show you on the bottom here, we show you some of the chemistry of this process. So you can see on the bottom left, we've got a simple hydrocarbon-based polymer. We're going to expose it to chromic acid, which is a strong oxidizing solution. In that process, we're going to introduce some chromic acid species. These will react with water in the solution. And in the end process, we'll add either OH groups or C double bond O, or indeed both. So we're basically going to provide some active chemical sites on the surface as a first part of the process of developing antimicrobial materials. So the first thing we did was to look at the surface chemistry of the materials that we've prepared. So as I said, we've actually surface treated these materials. We've actually put some oxygen functionalities on them. And the first thing we're going to look at is on the bottom left. I want you to look at the image on the bottom left here. And on the bottom left, you can see two images. One image on the bottom right, which I'm circling with my mouse that I hope you can see, is the untreated polyethylene. This is the material as received. And that single peak you can see here, which has got a C bar, C represents the carbon atoms that are bonded to other carbon atoms in this particular material. And what this piece of information shows us that on the surface of the polymer, and typically in just a few molecular layers, we simply have carbon bonded to other carbons. There's no evidence there of carbon bonding to oxygen. So this is the as received material prior to it being treated. If we look on the image to the left, we can see the surface chemistry of the material after 30 minutes etching in chromic acid. And what you can see is that the spectra, which was a single peak at the start, has now stretched quite a bit to the left. And the small extensions on the left that we can see that we've highlighted with these red curves, they represent the presence of carbon that's connected to other chemicals. And to be specific, it's connected to oxygen chemicals. So we've got some evidence here for carbon connecting to oxygen, carbon double bonding to oxygen, and also carbon bonding to oxygen twice. And that's important for forming carboxylic acid groups. So what this says here is that there's evidence that the oxygen groups are now chemically formed on the surface of my hydrocarbon. So basically, I look like I've changed the surface chemistry of my material. If I look over here on the left, I've also got a measure of the composition. This tells us how much carbon, oxygen, and other species are present in our materials at the surface based on how long we etch them for. So the set of data on the left shows the as received material. This material has received no etching, and we'd expect to see only carbon species. And of course, what we see here is just carbon species. But we can see here, as we increase the etching time, we can see substantial amounts of oxygen. Oxygen is shown by the white bar. So we have a lot of oxygen on the surface now, and some other trace molecules as well. But we're seeing a lot of oxygen on the surface, and this indicates that we have also confirmed the presence of oxygen. We're showing a bit of spectroscopic information here. This is infrared spectroscopy. This is not very surface sensitive, but it gives us some idea over a few microns what sort of chemistry has happened. And what we can see here, if we look at the light, look at what's in black here, we can see a flat line across this area here of about 1500, 1400 wave numbers. But as we increase the oxidation time, we go down to the green, we can see a broad band appearing here at about 1600 wave numbers, 1500 wave numbers. And that band shows the presence of some oxygen species. And the final test we have, which is a very simple test, but an important test to check that we've changed the surface chemistry, is we put a droplet of a liquid on the surface of our polymer. And typically we'll use water. Water is a material that we quite often use to check the surface chemistry of solids. So what we've got here is, in blue, are the contact angles, which is the angle a droplet of water makes with the surface. And the first data point on the left is for zero treatment, i.e. the as received polyethylene. And you can see here that the contact angle for this material is basically about 90 degrees. But once I've treated it just for a few minutes, the contact angle drops from 90 down to about 45 degrees. So what that says is that the water is much more compatible now with the polymer, and that's because the polymer has been oxidized. So the change in surface chemistry affects the way liquid droplets interact with the water. So it's a very simple way of checking the surface chemistry of our material. So far we've talked about the material, and let's move on to talk about what we do with the materials afterwards. And just to show you a photograph here, you can see here some droplets of water on our treated material, and the angle that those droplets make there, it's basically about 40 degrees. So this is what happens if you've got treated polymer. So treated polymer is more compatible with water, a smaller angle of contact. So what we're going to do now is start to talk about how we characterize the process of bacterial attachment. So what we do is we're going to take the polymer samples that we prepared. So these are small pieces of polymer, small coupons to be precise. We chemically treat them, and then we're going to put them into a solution that contains the bacteria. We're going to wait 30 minutes. We're going to take the coupons out. We're going to rinse off any bacteria that are not attached, and then we're going to stain them with some fluorescent dyes. And these dyes will basically attach to the DNA. And then we're going to image the surfaces using a special spectroscopic technique, microscopic technique called Confocal microscopy. And we're going to use a couple of dyes to do that. We're going to use two different dyes, one called cytone 9. This stains the targets or the cells. If they're dead or alive, the cytone 9 will see them. And we also stain the cells that had been damaged. And these ones are stained with a different dye called propylium iodide. So by using these different stains, we can identify the presence of cells and the presence of cells that are damaged and probably not viable. So we're going to take a series of images to look at the surfaces after they've had the aeruginosa attached to them. And we're going to look to see how much of the surface is coated with the cells, and also are the cells alive or dead. So that's the idea. We're going to be doing that experiment. And within the experiment, there are two actual assays we do. One assay is an estimation of how much of the surface is covered. So if I've got a lot of bacteria, maybe I have 100% coverage. And if there's very little bacteria attached, I might only have a few percent coverage. And as well as looking at the amount of coverage, we'll also look at the assay of the viability. In other words, are the cells that are there, are they alive or are they probably dead? So those are the two measurements we're going to be doing. There's a photograph coming up. This is the machine we use. This is Naima, one of my former PhD students. This is her using the confocal microscope for the study. It's quite a sophisticated piece of equipment we're using here, but it allows us to see single cells on virtually any surface you like. And they're not easy to see at the best of times, but this confocal microscope allows us to see them and also to image through the sample to see both the top of the cells as well as all the way down to the substrate. So let's talk about some of the first data sets. So what we've got here is some images for some polymer samples, and each image we've scanned about 400 micron by 400 micron area approximately. So we start by examining a sample that's got no biofilm on it. This is a polyethylene that has not been dipped in a solution, so there should be no cells there. So if we look on the bottom left, this is basically a control experiment. And what the control experiment says, if I don't dip it in the solution, there are no bacteria there. Well, of course, that's what you expect. So the first experiment I'm showing you is PE, and this is PE that's not been oxidized, untreated. I dip it in, I wait 30 minutes, I take it out, I wash it, and you can see these white areas here. The white areas shown in this image represent bacteria attached to the surface. And these bacteria are sufficiently attached that you can't wash them off. So they are quite robustly attached. So what we do is we do the same test, but of course we've got different polymers with different treatment times. What you can see quite clearly here, by the time we get to 30 minutes, we have a lot more black, much less white, which in short means there's a much lower concentration of bacteria. So the effect of simply oxidizing the surface means that less bacteria are attached to the surface. And that's plotted in the graph you can see above. So by the time we get down to our 30% treatment, we have probably something approaching about 10% of the area attached. So certainly it's not as clean as the material that didn't see any bacteria, but it's probably 4 to 5 times less bacteria than the as received material. So that's the attachment, that's the population of species. So the second test we do is we look to assess the viability. So of the cells that are on the surface, are they alive or are they probably dead? And these experiments involve us looking at the images from two different dyes. So there's a cyto9 and a PI dye. And from those data sets, we can estimate the amount of viable material present. And what we can see here is that there's some scattering the data, but when we have very little treatment, something like 30% on average of the bacteria are viable on the as received material, or even a very short treatment. But a material that's had a 30-minute treatment, the viability is very low, maybe 1 or 2%. So there's again something like a 20% reduction in the viable numbers of cells, just simply by treating the polymer and oxidizing it. So we can see here that for Pseudomonas, which is an important challenge molecule to consider, the simple treatment of oxidizing the polymer surface already has quite a substantial impact on the viability and the number of bacterial cells that are attached. Well, of course, we also had a look at some other bacteria, looked at a Staphylococcus and E. coli. Similar experiments, we looked at the effect of etching time on the viability of cells. And what you can see in the graphs that I'm showing you here at the moment, that for the Staphylococcus, there was a decrease in the viability from about 70% down to about 20%, so a reduction of about a factor of 3. And in the case of the E. coli, a reduction of maybe a factor of 50 to 60 in terms of the viability. That is the population of viable cells we can see on the surface. So the short conclusion from this section is that even for other bacteria that are quite common, these simple oxidation processes, changing the surface appearance of polymers, can certainly indicate some improved performance around antimicrobial behavior, which is encouraging. As well as actually looking at the bacteria on the surface, we also do another experiment called flow cytometry. And in this experiment, we are actually going to take cells that are on the surface, we're going to wash them off a little more aggressively, and we're going to look at the chemistry or the viability of those cells. So in other words, we are taking cells that were on the surface, we remove them, we redisperse them into a solvent, water, and then we measure their biochemical properties using a flow cytometer, which is a very common way of classifying cells. We add a special dye chemical to them, and what we can see is that there are two sets of results. If we look on the left, we see a green peak, and that relates to the material that is untreated polymer. And the cells that are being in contact with the untreated polymer, and the data to the left particularly, means those cells are predominantly viable cells. If we look at the sets of peaks to the right, those peaks relate to cells that have also been in contact with the surface of the polymer, but these cells are generally non-viable. So what you can see simply here is as we go from the PE, where the cells are all on the left and are viable cells, the cells that are in contact with the polyethylene that has been treated, those cells are much less viable. So which sort of confirms independently that the oxidized polymers affect the viability of the cells. So the cells are being compromised by the surface chemistry of the polymers. So far, I've talked about fairly simple methods for characterizing and modifying polyethylene, but we also have some slightly more sophisticated approaches because there's a long way to go from simply treating a polymer in the way I've described today and making that a viable long-term solution for improving antimicrobial behavior in a hospital or home application. And we know from other experiments I won't talk about today that some of the treatments I've described, although interesting, may not provide long-term relief from an antimicrobial perspective. So we've been developing a range of other methods which are slightly more advanced in their antimicrobial behavior. And these involve essentially attaching nanoparticles onto the surface of our polymers. So in other words, we've got our polymer, we're oxidizing them, and we're now looking at the presence of different particles on the surface. And many people have looked at magnesium oxide, zinc oxide, titanium oxide. Many people have looked at particles to do this, and we've been doing a similar thing. And we've been looking at this approach as a way of improving the performance, particularly in the long term. Because obviously, if you modify a surface, there are some examples, for example, a disposable piece of laboratory equipment or disposable apron, where it's only going to be used once, in which case the treatment I've described before may well be suitable. But there may be other applications in hospitals or other locations where you may want something to possess antimicrobial behavior for many weeks or months. And therefore, we're looking at two different treatments here, which we're not going to talk about the details of, but we'll call them Film A and Film B. And they're basically nanoparticles that are attached to the surface, and we're also assessing their antimicrobial performance as well. So just some images are over here on the right. So these are atomic force microscope images. And what we can simply see here is that the surfaces are relatively rough on a molecular scale, and the little bumps that you see here, they represent particles that are attached to the surface. So as I said, we've attached for a solution some very small particles, and these particles are paced between sort of 10 and 20 nanometers. So we talked before about microns. A micron is 1,000th of a millimeter. We're now talking about a nanometer, which is 1,000th of a micron. So these are very, very small particles. These are just a few hundred molecular dimensions, molecular diameters in size. And we've looked at these materials, and we're able to show that these materials, they do absorb on the surface. We can check that they stay on the surface. We've done some rinsing studies, so we know that they actually are there. So we're actually able to do similar surface chemistry that we did with the oxidizing before by adding these metal oxide particles to the surface. So we're not going to spend too much more time on the chemistry of that. We'll talk about whether they work. So here we've got some data both on viability and attachment assays for Pseudomonas again. So in this case, we've got different sorts of surfaces. We've got our polyethylene surfaces, but now we've got them with different, some with no actual sols or colloidal particles on them, and some with film A and film B. And if you look at the images there over on the left, you can see we've got some modified materials. And this represents no oxidation, 10 minutes, 2 minutes, 10 minutes, 30 minutes. So what we're seeing here, the best performance we reported was the following. If we took our polymer, we oxidized it, then if we treat it with our nanoparticles, we get the best possible performance. And you can see here the levels with the sol, you can just see here, are much lower than when there is no sols. In other words, this is just a polymer by itself, which is good, but the sol, it's even 5 times better. So even though the results we showed earlier showed good performance for oxidizing the polymers, the introduction of these metal oxide particles offers even superior performance. So certainly the attachment levels are much lower. And over here on the right-hand side, we have viability experiments. And generally speaking, there's lower viability for the surfaces that have got the films A and film B. Only slightly better viability. Much better attachment performance, slightly better viability performance. In other words, the nanoparticles overall add a positive dimension to the antimicrobial performance of our polymers that we're looking to treat. So we've also done some experiments where we've left our treated materials, this is our treated polymers, and we've left them inside water for 24 hours. We want to see, well, I've got my treated material. If I was to expose it in water for 24 hours, would I still have my antimicrobial behavior, or would I lose it? There's a lot of data shown here, but the short answer is for my simple oxidized polymers, I'm going to lose a lot of that performance, I'm sorry to say. So even though if they aren't exposed to a lot of water, they perform well. If I take my polymer that's treated, I expose it to water for a day, I lose a lot of performance. However, the good news is for the materials where I've got the colloidal particles present, I don't lose my performance. So in other words, the colloidal treated polymers perform much better in the long term. So we can see here that modifying polymers is useful, but modifying polymers and then attaching special nanoparticles is even better. So we've been talking about polymers, polypropylene and polyethylene, which are the standard polymers, but we've also done some work on polycarbonate, which is another commonly used, more high-tech polymer. And you can see here we've got some data showing that for polycarbonate, you also get good performance, okay? And that material doesn't require any oxidation. Polycarbonate is naturally, has a lot of oxygen present in it already. And you can see here that you get good performance. The film B was the best material, and polycarbonate untreated was better antimicrobially than the cheaper polymers, polyethylene and polypropylene. Although when we treat it, we get best performance. So your options are, you either take polycarbonate, treat it with our special colloidal particles, and that works, or you take the polyethylene, oxidize it, then you treat it with the colloidal particles. In each of those two scenarios, you get good performance against Pseudomonas aeruginosa. So the clock is running, and believe it or not, it's coming to the end. So what we can tell you is that hydrophobic polymers such as polyethylene are ideal hosts for a range of bacteria. This is not news. We all know this, but the studies confirm this well-known fact. However, if we treat polymers with acids, making them more polar and acidic, we can improve their antimicrobial performance. However, it turns out that their performance, although improved, isn't necessarily best in the long term. However, if we act by using a metal sol to further chemically modify these polymers, we get even better performance. And those performances probably provide much better long-term promise. So there's quite a bit of work to do yet to take these polymers to deploy them into real environments such as hospitals or homes or food places to see if they work in the real world. But they, from a laboratory perspective, offer promise as low-cost surfaces with antimicrobial properties. And the important people to thank here are all listed above us, and particularly like to highlight Fatima, who did all the hard work. I'm just happy to report her good work, but she was the actual person who did all the experimental work. So I thank you for your time and attention, and I'll be happy to pick up any questions via the chat or by voice if you're able to do that. Thank you for your time. So I can see a few questions here at the moment. And so the first question is, this person was asking about the shelf life and lifetime of the modified PE, and can you give the ratio compared to the unmodified? So I think one of the things I highlighted a bit later on was that the modified polymers, just modified by this case by oxidation, don't have a great shelf life as far as exposure in water. We don't at the moment know what their exposure is like when they're actually in the environment, which is something we will check. So if I took a polymer surface, if I left it outside for a week, then I checked it antimicrobial behavior, what would I lose? We will need to look at that. We haven't done that yet, but we certainly are looking to do that. Someone's asked me about COVID-19. Will it work with viruses? Short. We are currently trying to arrange some work with some colleagues in another department to test our materials against COVID threats. So will they work? The answer is I don't know. They might. And we are hoping with the next month or two, we'll have a chance to check them out and to see if they're able to have some effectiveness against those sorts of viruses. Could you share the pluses and minuses of using metal oxide coatings compared to metal ones to medical applications? The big concern in the use of any sort of metal containing material is that the metal will leach out. The medical world are very concerned about putting metal-based materials in contact with humans such that those metals could leach into the bloodstream or into the body and cause other secondary problems. So one of the things that we spent some time on is making sure that when you attach our colloidal particles to the surface, they don't leach out. And we are very confident that these colloidal particles, once they're attached, do not leach out. So that's one of the benefits. They don't leach out. And the other benefit is that if you take a lot of metals, sometimes they will react. Sometimes you'll form things, complexes, they'll dissolve, and those dissolved materials will in the end transmit themselves into the patient, which you may not want. So we like the metal oxides because firstly, the concentrations are very low. We're talking about a 20 nanometer layer. So the concentrations are nominally very low, and they don't seem to have much risk of leaching, which is important. Another question was there a sign of discharging of colloids from the colloidals to the water? So I think I just pretty well answered that question. The colloidal particles, once they're coated, we wash them initially to remove any excess material, but once they're initially washed, they stay there very, very robustly. So they're very strongly attached. So they don't leach out. This is the good, and we have had a good look at leaching. How would polyethylene be modified if possible via nanolithography? There are lots of really clever ways you can modify polymers like polyethylene. We aren't using them, not because we don't like them, but because at the end of the day, we want to make affordable solutions that have societal impact. And as much as it would be very exciting, we might get a Nature paper by making some very clever nanolithographed prepared material, it wouldn't almost certainly be viable. We couldn't make that sort of material and coat a bed in a hospital or an important piece of apparatus in a medical clinic. So we're looking for materials that are not only low cost, but are also scalable solutions which would allow us to deploy these in real world applications. So this is, and that's one of the reasons we're working on really simple materials, because these are low cost. If you can modify them inexpensively, then they have a wide range of potential applications. So even though nanolithography is very exciting, it's probably not practical for large scale applications. So good question here. What could be the reason for the loss of antimicrobial properties in the PE compared to the colloidal treated? So why have we lost some of our functionality? That's a good question which we're going to have a look at. My concern would be that we're absorbing, so when we take our sample and we put it in water, our treated polymer, put it in water, there's a risk that any contaminants or any other materials in the water will come out of the water and adsorb on the surface, on our polymer surface. So my main concern would be that our sites, the polymer sites we've created, have attracted other molecules. For example, there are other contaminants, surfactants, other things in water naturally. And if the molecules were attracted out, they might block our surface sites sufficient that we lose our performance. It's a good question. We don't know if that's the reason, but certainly I think that's probably a potential explanation. I'm just seeing some more questions here. Right. Is it possible to use the antimicrobial polymers in water treatment as an alternative? I think if you're talking about water treatment to kill bacteria in water, a good question. We have another project, which I'm not talking about today, where we're working on materials for doing that. But they could play a role. So the short answer is yes, but we are developing another class of materials specifically for water treatment. This is for water treatment. This is for preparing, this is for having antimicrobial surfaces for home, for hospitals, for clinics, for example. But we have another project where we're looking to develop materials which specifically are designed to kill bacteria that are in water supplies. And some of these particles could have a role there. So yes, it is possible. I'm just checking I've answered all the questions. I think we have. If anybody's got any questions they want to ask offline, which sometimes is the case, do feel free to email me at the university, d.r.williams@imperial.ac.uk. I'll be happy to pick up any questions offline if that suits you. I thank you all for your time and attention, and I think we're probably going to be wrapping up. Does that sound right, Leah?
Yes, thank you so much, Daryl, for such an informative presentation, and also for getting through so many questions. That was really great. The recording of this webinar will be put up on the IMSE YouTube channel very soon, and you can find the link to that in the chat function, as well as all the other links that I put in there. So the next webinar in this series will be on the 20th of June at 2 p.m. On the theme of lymphatic system transport and vaccine adjuvants. So this will be presented by Professor James Moore. Next week, we also have a webinar in the Greener Plastic Futures and Sustainable Materials webinar series, and that's on Tuesday, the 23rd of June at 2 p.m. And that's by Dr. Gonzalo Gozal. And this is on optimizing sustainable chemicals and fuels using processes of system engineering. So thank you once again to Daryl for such a great presentation and getting through all of the questions, and I hope everyone has a great rest of the day. Thank you very much.
Okay. The suitable sterilization methods that can be used for PE with the metal-oxide film. The answer is we haven't looked yet to see whether our materials will survive sterilization. The reality is that a lot of polymers in this application space, in some cases, it's one-use only polymers, but we certainly are used to autoclaving materials, and we will probably try some autoclaving experiments later on to see if they survive that. But that's a good question.